Good afternoon, everyone. I'm Thomas Bertin-Moreau from Corning. I have the pleasure to share this session around the IGU technology. I would like to thank the presenter because getting a presentation right after the lunch, by experience, it's a tough job. So let's go ahead and get started. I would like to introduce Uwe Risle from Glaston in Germany. Uwe is a mechanical engineer by training with more than 20 years of experience in the equipment OEM industry. He's currently a director of product management at Glaston, again in Germany, for the product related to the architectural glass. And Uwe today going to talk about a very interesting topic around the longevity of thermoplastic spacer compared to other spacer technologies. Please, Uwe, the floor is.
Thank you very much. Also, welcome from my side. I hope you had a good lunch also from your side. And I want to present you the presentation of longevity of Thermo Plastic Spacer. And let's have a quick overview about the agenda of this presentation. First of all, I want to make a briefly introduction of the insulating glass unit. Then the application process, I want to explain a bit more. Then, of course, a reactive miracle, so-called the TPS or Thermoplastic Spacer, and a small outlook and summary. Let's talk about the insulating glass components of an IGU. These, of course, are at least 2 glass panes, or 3 glass panes, or 4 glass panes. Then we have a spacer. The spacer keeps a distance between these 2 glasses, or 3 or 4 glasses. Then we have a desiccant filling particles inside the spacer. And of course, we have primary sealant and secondary sealant. Then, of course, the cavity has, let's say, filled out of gas. Yeah. Most common is here the gas argon, because of the low price of argon, good insulation capability, and common utilized gas. If you want to have better performance, you can also use krypton or xenon, but this is then higher price, but also higher insulating capacity. Let's have a closer look to the sealant. You see in this graph that there are different sealant types. One sealant type is a primary seal, is butyl. Then we have polysulfide, we have hot melt, we have polyurethane, and we have silicone. These are two component systems. And of course, every sealant has argon diffusion on a special type. And of course, you see with silicone, you have a big diffusion of argon gas during the lifetime, and therefore it's very important that the primary sealing will hold the gas inside. The spacer has a function. Of course, the spacer keeps a distance between the glasses, enables absorption of humidity. Of course, it should be flexible in order to absorb stress caused by thermal expansion and contraction. Yeah, spacer types are many on the market. You see this here. There are, let's say, the biggest group are the box spacers with steel, stainless steel, Thermix, TGI. These are a very big group and still very common in the insulating glass industry. Then we have the flexible spacer. It's, maybe the super spacer, which will be applied on the super spacer applicator. And of course, we have an application system. This is then our TPS applicator, where the material can be applied directly onto the glass. Let's have a deeper look to the TPS material. TPS spacer combines all of the major advantages. It's an integrated spacer with desiccant and primary sealant into one single material. Then we talk about the application process. You see here our application process. There are worldwide more than 250 lines running with this application system. The material comes out of a drum. Yeah? It will be applied from a nozzle side, and the big advantage it has is that you have, let's say, a flexibility in an application, because the spacer width that you can apply is from 1 by 1 millimeter, and therefore it's a CNC controlled machine, 24 hours, 7 days machine. So this is really something what needs not an operation anymore. It's a really automatic system, and this is very requested from the market right now, because everybody has a lack of operators, and therefore the machine is brilliant. You see, we're making also the bevel joint, so-called bevel joint, in the corner to keep, let's say, this application gas tight at the end and at the beginning, and this is the big advantage of this. So TPS is not only a spacer, it's a reactive system, and therefore it's a reactive miracle. It's based on polyisobutylene, which bonds chemically to the glass and bonds also chemically to the secondary sealant if it's silicone. That means it creates a stable, inseparable structure. The spacer cannot be displaced even under stress over time. It also withstands temperature up to 90 degrees C and resists chemical incompatibilities in the glazing system. Insulating glass units are exposed to a variety of stresses during their service life. This includes extreme temperature changes, humidity levels, wind loads, and different pressures. All of these factors affected the edge seal and the internal airspace. TPS helps maintain the integrity of IGU by absorbing stress and limitation of structural deformation. This extends the lifetime of the unit and reduces the risk of early failure. Oh, what's happened there? Stress on IGU always leads to strain, and how the unit handles the strain determines its longevity. Rigid spacer systems rely on the deformation of the glass or the sealant to absorb this strain. TPS behaves differently. It can deform elastically, distributing stress more evenly and preventing long-term damage. Its chemical reactivity strengthens the overall structure, reducing weak points and minimizing the chance of seal failure. Then you see also the better moisture barrier and the gas barrier. TPS provides this also if you have, let's say, thermal contraction by different temperatures in and outside. Compared to traditional IGUs and foam spacers, TPS drastically reduces gas loss and moisture ingress because of much more contact onto the glass pane. This enhances insulation and preserves the unit thermal performance over time. One of the biggest benefits you see here is the continuous seal, and it creates a really chemical bond itself. This is so-called the bevel joint, which will be applied on the glass either in the corner or on the straight line. This eliminates potential leak paths and ensures long-term gas retention and moisture protection. It's totally different to the other two on the lower side on the picture, where you can see big problems in the corner. Thermal insulation relies on three factors. You see this here in this pyramid. This to increase the thermal performance. The biggest one is the low E. Low E coating brings a big effect to have a good isolating glass unit. Of course, then it comes the argon filling as a second part, and then also the warm edge spacer as a third part. Of course, the warm edge spacer is only a small part of this, but if the warm edge spacer fails, the other also are failing. Therefore, in this pyramid, all three partners must work together to get a really good performance out of this. This chart shows the correlation between UG values and argon concentration. As the gas concentration drops, the insulation value is getting worse, the UG value increase. TPS helps prevent this by minimizing argon loss over IGU lifetime. Maintaining high gas concentration is critical to long-term energy efficiency, and TPS supports this goal. TPS ensures long-term cavity tightness even under challenging environment conditions. Because the material remains flexible over time, it can adapt to thermal expansion and contraction without breaking the seal. The adaptability helps preserve the gas fill and maintain insulation performance for decades. It's one of the key reasons TPS is used in high-performance IGUs around the world. TPS has undergone very big testing in accordance with EN 1279 Part 2 and 3. In these tests, units are exposed to extreme cycling conditions, ranging from minus 18 degrees C to plus 80 degrees C with high humidity. Each cycle simulates years of real life. Even after 5 cycles, which represents decades of stress, the TPS seal remained intact. This confirms that the system is reliable not only in theory, but also in extreme practical use. In addition to the laboratory tests, TPS has been tested in real buildings. This table shows argon gas concentration measurement taken over a period of 3 years. In all 8 tested IGUs, the argon values remained high and stable. The average improved slightly, reaching over 96%. This real-world validation shows that TPS maintained its performance even after years in fully operational environment. TPS plays a key role in maximizing thermal efficiency of isolating glass units. It combines 3 critical factors: low thermal conductivity, high gas retention, and warm edge performance. When compared to traditional aluminum or rigid spacer, TPS drastically reduces energy loss through the edge. This helps building maintain a comfortable indoor climate while reducing heating and cooling costs, as you see here this in a photo, more or less. As a summary, Thermoplastic Spacer longevity, a solution to meet requirements due to lean production, is possible, increasing requirements in energy efficiency worldwide, high insulation effect, and due to excellent properties of the material, the reactive material for TPS is also established in the solar industry. So this was my presentation. Thank you very much for your attention. And if you have some questions, please.